Okay, so let me check my notes and see where were we. Okay, so we want to start now. We want to start now. Okay, here we are again. We have been talking about this is a kind of introduction to mathematical logic. Again, this is completely based on the book by Tao, and you can read it by yourself. I am trying to to add examples and improve, or I guess make it worse from time to time, the text or the explanations, because it's actually difficult to improve what is written in this book. But I am using other books as well, and but in any case, this is something that you can do by yourself. So far, we have been talking about, if you remember, I have introduced to you we have started with the mathematical statements and what a statement is, what an expression is. So you remember that. So 1 plus 1 equals 2 is a statement, but 2 times pi times square root of I don't know, 32, for instance, is an expression. Okay, and you can make statements out of expressions by using relations, and you know a lot of them, even though we have not yet introduced them, right? Like these kind of things, you know all of them, even though we have not introduced them, right? Or by using properties, for instance, is positive, is negative, or whatever. And you can make a compound, remember, compound statements for more basic, for more primitive, if you want, statements, by using logical connectives, such as if, then, if, not, if and only if, and so on, right? Now, again, and I cannot say this enough times, logic is concerned with truth, not efficiency. So sometimes these things will be very long and tedious, but it is a good way for you to get to get used to use logic, and logic, of course, is a very powerful instrument. Now, we then talked about, come to delete all of this, we talked about conjunctions, right? Remember, if X is a statement and Y is a statement, then X and Y is a statement which is true if X and Y are both true, and otherwise it will be false. We have talked about disjunctions. So this was a conjunction. Remember, con with junction. And then we have talked about disjunctions. Sorry about my calligraphy. Disjunctions. And this, remember, means something like apart, right? So X or Y is true if either X or Y is true or both. For instance, 1 plus 1 equals 2, or I don't know, 2 plus 2 equals 4 is true. But say 1 plus 1 equals 4, or 2 plus 2 equals 4 is not. The whole statement, this disjunction, is not true. Now, remember, and I spent quite some time about this or, right? So in mathematical logic, or in most of the cases will default to inclusive or. So this or is an inclusive or. What does it mean? Remember that x or y is true. So let me write it down. So if you have A or B, okay. So this disjunction will be true in the case in which this or is inclusive, meaning that x or y is true. Sorry, A or B is true, or both of them. Now, if that or was exclusive, then this disjunction would mean that A or B, not both, or either A or B, right? So exclusive means that one of the two is excluded, while inclusive or means that A or B is true, or both of them. And that sometimes can be a bit confusing, at least for me. Now, we moved on, and from conjunction and disjunction, we moved forward to negation. Negation. So, the statement A is not true, or A is false, or it is not the case that A is called the negation of A. And it's true only if A is false. And it's false if and only if A is true, right? Because we're negating it. So if it's false, then the negation is true. For instance, it is, let's say, 2 plus 3 equals 10 is not true. Sorry. So this statement, as you can see, is true. This negation is true, right? Of course, we could have made it much shorter by writing 2 plus 3, which is not 10, right? But it's the same thing. An important thing about negations, and really please remember this, because this could be important when we start to prove theorems and such, is that a negation converts N into O and the O into AND. This is I explained this in the previous lecture, and I'm not going to spend time talking about this. So please watch the previous lecture to check that. So if you have a statement, and that statement contains here an or, a negation, and if you negate that statement, that or will turn into an and. So something, 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 something. And the negation, vice versa, will convert that and into an or. Okay? Yeah. And this is where we left it last time. And this is where we're picking it up again. So remember, for instance, Shuehao is late, or Shuehao is lying. What is the negation of that? Zhao Xiaodong.
Xuehao isn't late and he's not lying.
it would be 说好 so what did I say? I forgot. 说好 is 说好 is late or 说好 is lying.
Yeah.
So the negation of that would be 说好 is not late and yes 说好 is lying.
The second sentence didn't change. I think it will change.
Yes.
It should change.
Well done. Yes, yes. As I told you, I'm constantly trying to confuse you on purpose.
Yeah.
Or
Yes.
I am making mistakes. So yes.
Yeah.
Yes, yes. So yeah, 说好 is not late and he is not lying. Right. Now, let's use an example which I took from Tao. So if x, say x is a real number, so what is the negation of x is larger or equal to 1, or x is less than or equal to -1? What is, so we take this statement and we want to make a negation. So what is the negation of it? Someone?
X.
X is smaller than 1 and x is larger than -1.
Are you sure?
Yeah.
Did you cheat? Did you look into the book?
No. By the way, I think we have done this kind of exercises in our high school.
Oh, well, I am then extremely happy for China. Really.
Yes.
Awesome.
We think almost all of us have done this kind of exercises.
Okay. Okay, then I can move forward much faster than I thought. This is very nice. Really, I'm very happy. This is not the case in Spain and in many other countries, unfortunately. Okay. In any case, a negation will produce a statement which could. It is possible that a negation produces a statement which could not possibly be true. For instance, if you consider that x is an integer, the negation of x is either odd or even is, of course, x is neither odd nor even, which is not true, right? But that's fine. That's fine. There is something which can happen. Negations are sometimes very complex. We have been dealing with statements which have been, with negations which have been very easy to, to work with. But consider, for instance, the following. If I told you, let's work with multiple negations, for instance, it is not the case that either A is not equal to 3, nor larger than 1, nor odd, but not both. So this is a statement which can be very confusing to work with. I just said something randomly, by the way. I didn't check it. But what I mean is that negations, when you compound them, they can be very confusing. The nice thing is sometimes, or very frequently, negations cancel more than one or two negations at a time. For instance, if you say X is not true, the negation of that is just X, right? So if you want to negate X is not true, the negation of that is X, simply that. Now, let's move forward. And since you did this in high school, I am going to move a little bit faster. We want to see now if and only if. By the way, if you think that this, so if you think that this is a waste of your time, please let me know, and I will move even faster. So now we say that, so if you have two statements like A and B, we say that A is true if and only if A is true. So you say that whenever A is true, then B has to be true. And also, whenever you have the case in which B is true, A accordingly has to be true as well. So the two of them are logically equivalent statements. So I'm going to write it down. Logically equivalent statements. And this is a lot of fun. I like this a lot. For instance, if X is a real number, then the statement X equals 3 if and only if you know that it is written like that, right? 2x equals 6, right? So saying one thing is equivalent to the other one. The two statements are logically equivalent, they are connected. Okay. But the nice thing is that statements that are equally true, they are also equally false. And also, two statements which are equally false will also be logically equivalent. For instance, 10 and 1 equals 14 if and only if the square root of 2 equals, I don't know, 10. Anyway, okay, then you have on page, so this is the appendix, remember that? And you have a series of exercises, and I would like you to do them, which go from, so this is appendix A, so it is, so it's, I'm talking about the exercises from A11 down to A16. Okay, so please do them. Okay, very nice. And with this, let me check my notes on the book to follow the same, yes, the same logic, which is fun in the chapter about logic. I want to say, what I mean is that I want to follow exactly the same thread, the line of thought. So the second point that I want to talk about is implications. Yeah, and this is not very intuitive. Implications. Yeah, I like a lot philology, as you know, and when you look at the word, you can realize where this is coming from. This is an in, actually, and here we have a word which we have actually an stem, which you find many words like explications, applications, etc. And by checking, or in your case, you cannot do that because you don't speak any Indo-European language. But the advantage of speaking in European languages is that you realize sometimes very easily about the meaning of the word, even if you don't understand the mathematical definition, if you know a little bit of Latin and Greek. But anyway, so implications are not very intuitive. This is a logical connective. Remember, we have seen different logical connectives, but I want to talk about implications. If A is a statement and B is a statement, then if A, then B is the implication from A to B. You can also say A implies B, or A is true only if B is true. Okay. What this means depends on whether A is true or false. If A is true, then if A, then B is true. When B is true, and false when B is true. You see that, right? So this statement is correct or true when B is true, and this statement is false when B is false. If, however, B is false, then this statement is always true, independently on whether B is true or false. Right? Ciao, Xiaodong. You look confused.
Yes.
Okay, that's fine. But you should interrupt me if you don't get me. Don't be afraid of asking.
Yeah.
So look, let's say for instance, if the student I'm talking about is Wu Tao, then I know that he has had some introduction about logic. So that implication is true because both, in this case, both A, the student is Wu Tao, and B, he has had some introduction on logic, are both true. But if I said, if this animal is a chicken, then it can fly. This statement is wrong. It's false, right? It's fine. So a chicken is a chicken, so that's true, because chickens are animals. But we know that the chicken cannot fly. So B is responsible for making the whole statement wrong. False, sorry, I should say. But if I said, if this animal is a green chicken, then it cannot fly. B is completely true. But since A, which is a green chicken, being an animal, is always false, then the whole statement is false. Right? Okay. Yeah. So if A is true, then if A then B implies that B is true. But if A is false, then this statement does not tell you anything about B. Is it true or is it wrong? We don't know. So if this is correct, you are fine. But if this is wrong, if this, sorry, should say false, If this is false, then you don't have any idea about P. In that case, when this happens, we say that the statement is empty, or if you want, vacuous, like a vacuum cleaner or the vacuum, right? So the statement is vacuous, does not tell you any new information other than what you already had before. If this animal is a green chicken, and we know that this is already false, then I like ice cream. Well, since I am departing from something which will never happen, I don't know what this statement is telling me. It will not give me any new information, and therefore the implication is vacuous. Tao, just out of curiosity, did you see these kind of things?
Excuse me?
Out of curiosity, did you study this kind of things in high school?
Yes, I think we have studied this kind of things. X can derive B, B can derive A, or X, or both of them
We
can.
didn't.
Remember.
But we didn't.
You didn't.
We have not studied this vacuous thing.
Okay.
I think it's just an English word. If we can translate it, maybe
Okay.
something we have learned. Sounds like something we have learned.
Okay. Let's look at an example now. Just to, because I find this extremely fun. For instance, if I'm going to take again, because I'm going to take the example from the book. Consider the following. If I don't remember what he had, but anyway, I'm going to continue with A and B. Now, if A is an integer, right? Consider that A is an integer. Okay, this is our statement. Now, the following statement, if A equals 2, then A squared equals 4. Now, this is my question for you. Is this true? Are you sure?
Yes, it is true.
Okay, but what do you know about X or A? Yes, he was using X. What about A? You don't know anything about A, right? We don't have, I'm not telling you anything about A. So the nice thing is that this statement is true regardless on the actual value of A. I don't know what is the value, the actual value. It could be 1,023,023. I don't care. But what this statement is telling me is the following. Okay, I don't know the value of A, but if it is true, then A squared equals 4, right? Now, this is extremely easy, but hold on, because it will not be easy later. Okay. Now, there are some special cases which we can practice. For instance, now the implication, if 2 equals 2, then 2 squared equals 4. In this case, we have that true implies true. Well, fine. But now, if I write here square root of pi equals to e to 23 divided by 2, then 2 equals 3. Is this statement true or false? Wu Yuntao.
I think it's not true.
Why?
I mean, we can only say this is true if the first is true, I think.
No. So in this
No,
case,
no,
you're wrong.
or we should divide the two parts.
No. It's like I'm saying, for instance, okay, consider the following. If 2 equals 3, then 10 equals 9. Are you fine with this? Is this correct? Is this true? It's a statement. Yes, it is. The implication is correct. False implies false. If green chicken
I think I have
exists, then elephants
way
can fly.
to judge.
Sorry, come again.
I think I have a way to judge from what we have learned in high school.
But
We can first inverse it and then make
no. Don't make it so complex. I'm just asking about the implication. So this statement, so this kind of thing is called an implication. This, then that. If this, then that. And what I wanted to explain to you is that, for instance, in this case, if 2 equals 2, then 2 squared equals 4, which means that true implies true. But in this case, if 2 equals 3, if you live in a world, in a very strange world, in which 2 equals 3, then 10 equals 9, because false implies false. The implication is correct, even if both small, so individual statements are wrong or false. False implies false. Okay, now consider the following. If minus 2 equals 2, then minus 2 squared equals 4. This is false, and this is true. And the whole implication
False.
is true. False implies
false.
true. No. The only thing, remember what I said before, this is the kind of implication that I was talking about before. These two last examples are vacuous. They're not giving you any kind of new information because their hypotheses are false. This is false, and this is false. If you depart from something false, then you arrive to something which is true. Well, I don't know. In any case, this is true, and this is false. But the whole implication is correct, even though it is not providing me with any kind of information. It's vacuous, it's empty. Okay. In any case, yeah.
What if, for example, if we force A to be 1, and then what about this statement? If A equals 2, then A squared equals 3, but we know that A equals 1. So
no, but the important thing is what you have written into this into these symbols, quotation marks.
Mm.
So the point is that the falsity of the hypothesis does not destroy the truth of the implication. It is actually quite the contrary. When you have a hypothesis which is false, and that we know that this is false, the implication of all of it, so the whole implication, the implication is always true.
So yeah, that's counterintuitive.
Yes, but it's just you need you need some time to develop a kind of intuition which you will ultimately obtain. So the only way to say that an implication is false is to show that that while the hypothesis is true, the conclusion to which you arrive is false. For instance, so let's back up a little bit. You see, I told you this will not be intuitive. If I tell you if 1 + 1 = 2, and I ask you now, is this false or true? This is true, right? Okay. So this is our hypothesis. This is the hypothesis of the implication. So this is the departing point of your implication, right? If a chicken is a class of animal, and we know that is true, right? Then 2 + 9 = -10. Now, this is true or false?
False.
People,
False.
yes. Are you doubting? Yes. Now, okay, we have that this is true and this is false. But what about the whole implication? Is it a true implication or a false implication?
False.
Yes, it's false. Because you know that your working hypothesis is true. So true must imply true. But here we have a false. So that the whole thing is false. I think that things are clear now. Yeah. So this let me see.
I mean, what if now the hypothesis is like 1 + 1 = 2? So what if the hypothesis is like A = 2 with a
that's
a
perfectly
label?
fine. The only no, A, no, because I don't know what is A. But if you tell me A, if the integer A = 2, then you have a working hypothesis, a true
For example,
hypothesis.
For example, if I tell you A = 1, A = 1, and now the hypothesis is A = 2. If A = 2, then 2 + 9 = -10.
Yeah, no, but Joao, the point is that you are thinking outside of these quotation marks. The only information that you have is in the is contained, embraced into this statement. You evaluate this with only the information that you have here, and then you evaluate this. If this is true, this must be true. And then the whole thing is true. If on the contrary, this is true and you see that this is false, the whole thing will be false. Okay? So true implies true. False implies false. And false implies true, which is the thing which was confusing you. If I tell you, Shuhao is a very handsome guy, and we know that's not true, because it's not the case, then blah, 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 blah. Whatever it is, I don't care what you tell me here. I know that the whole statement is false, because you are not handsome. I'm joking, you know that. Okay, or you can change your name with my name if you prefer.
Yeah, if I becomes handsome, because, for example, I made some surgery, if the hypothesis changes, then the statement
Yes,
true or
of
false.
course, but you cannot touch it. You have only the information. You know, this is the way. This is you have to get used to a correct way of thinking, which is why I was telling you, logic sometimes can be extremely tedious, but it is only concerned about truth. So you only check what is in between these two marks and evaluate that implication. Okay. Now, so another way of seeing it is the following. You can think that so if you have this box, let me back up. Okay. So you have those quotation marks. You have your hypothesis here, and you have your implication here, right? Now, you can think of this implication or this statement, this compound statement, as this box here is at least as true as this box here. So if the first box is true, then the second box has to be true. But if the first box is false, we don't know anything about two. It's an empty statement. You have a vacuum statement. Two could be as false as one, but it also could be true. I don't know it, and I cannot know it because this is the information that I have. Red equals green. Then the integral of x squared dx equals between, or something more complex, between minus 133 and 3,024 is 245. I don't know. I don't know. Well, in that case, I made a silly example because you can check it. But the point is that in this box, the second box, you are completely lost if this is false. You have a vacuous implication. Now, and then in the book, which is what I'm constantly talking about, there are other books, and I will mention them later, and which are extremely nice. But vacuous true implications, this is a vacuous, so the whole implication is true, but it's vacuous because you depart from a false statement, and then you say, if this, which is false, then that. The whole thing is true, but we don't have any kind of information. It's vacuous again. We are constantly using them when we speak. For instance, in many Romanic languages, we say this will happen when cows fly. Okay, so when cows fly, Shuhao will be handsome. We're constantly using that. Or in English, they say, hell freezes over, which is a false hypothesis. Now, there are more complex ones. Like, for instance, if because I'm talking constantly about Shuhao, I'm going to change my victim. It's going to be Zijian. If Zijian had checked his computer yesterday, then he would have been punctual today, on time, right? Because he had enough time. So this kind of statement is used in a situation in which you know that both A and B, or 1 and 2, are both false, because we know that Zijian did not check his computer yesterday and that he was not punctual today. But the implication, however, is true. So you see, false implies false. But the whole thing is true. He would have been punctual, and I would have been very happy. But he was not. You can use it, by the way, to see how contradiction works. Now, if you believe that if he had checked his computer, he would have been on time today, but you know that he was not on time today, what can you conclude? You can conclude that he did not check his laptop yesterday, or he's telling a lie, but that will not constitute the second thing, because he does not lie, right? So if he had checked, if he had checked his computer yesterday, he would have been on time today. It is impossible otherwise, and that would be a contradiction. So in this case, a vacuous implication, something which in principle cannot provide you with any kind of information, is actually used to derive a very handy truth, right? Okay. Implications can also be true even if they are not connected logically. For instance, I can say, I don't know, let's delete this. I can say, if square root of pi equals 0, then Beijing is the capital of China, right? This statement, this implication is true, but it's a bit strange. We are departing from something false, obtain something true. Are you fine with this? Another example is the following. If, say, if 0 equals 0, then Beijing is the capital of China. That's also true. It's a bit boring, but it's true. But if I tell you, if 1 plus 1 equals 2, then Chinese people speak Italian. What about this one? This is false, right? So the point is that this implication is false now, but it is unstable. I don't know, maybe in about 100 years, Italian becomes extremely fashionable, and all of you start speaking Italian. So all of China suddenly decides to drop Chinese, and that's a very, very confusing way of writing words for foreigners, at least half of the population of mankind. And then all of you start to write in Italian. So right now, this is false, but it is unstable because it could change. But in any case, what I want to say, and I think you have got the point by now, is that to prove an implication, oh, sorry, I get some, what is this? Yeah, some ads. Okay, so to prove an implication, if this, then that, you start here. You check your hypothesis. You assume that it is true. And that you use that information to deduce that. This is still a valid way of working, even if your hypothesis turns to be false. The implication, in the case in which this is false, remember, does not say anything about the truth of the first box. So the whole thing, the whole implication, is not, in the case in which A is false, is not guaranteeing anything about the truth of the first box. But it only guarantees the truth of the second box, B, conditionally on the first box being true. I know that the words are very confusing, but the idea is quite clear. If this is true, you could have here true or false. And the whole implication is only telling you that in the case in which this is true, then you know that this is true, right? Are you with me? Kind of? No? Yes? Should I keep on talking, or do you want to ask anything?
Paul?
Yes?
Did you, I'm just checking, did you just said the first one, if the first one is false, but we suppose it is true and derive that it is false.
Yes,
and
I knew that.
Say this is false.
No, I knew that, yes, sorry. I knew that this would be confusing. What I'm saying is that you can have, let me delete this. Okay. So this is our implication. And so how was being wrong before? Because he was working outside of this context, right? And I said, please do only check what is between the quotation marks, because it's all the information you have. And what I said is still correct. In order to check the validity of the implication. Now, once you have checked the validity of the implication, and you have seen that it is a valid implication, you know, okay, you know that this thing here, the implication, which is a statement, you know that your statement is true. Then you can use it to derive whatever you want to derive. You can play with this to see what happens here on the right. And if you manage to prove that what is on the left leads to a true on the right, then you are using the implication to obtain what you are trying to obtain, or maybe not. But the first thing that you have to do is to check whether your implication is something that you can work on. Is this something you can work with? If you can do that, then you can use it as a tool, but only later. Okay. So some examples now. Let me see. If 2 plus 2 equals 5, then 4 equals 10 minus 4. So, is this implication correct? True. This implication here.
Since the first term is false, I think it's always true.
Okay. Okay. So this is our hypothesis, right? And you have to be completely agnostic about it. You know what is it? Agnostic. Agnostic means knowing. And this A is not. So you have to be, this is why you say, do you believe in God? No, I am agnostic. It's a different thing to being atheist. Being atheist means that you are actually against the existence of God. And that being agnostic means I don't know. Okay? So you have to be agnostic about the hypothesis. Okay, let's assume that indeed 2 plus 2 equals 5, because this is our hypothesis. Okay. Let's multiply it by 2. Then we obtain that 4 plus 4 equals what? 10. Very nice. Now, let's subtract 4 from both sides. So minus 4 and here minus 4. So we obtain that 4 equals 10 minus 4. So, as you can see, the implication is true. 2 plus 2 is not equals 5. But if 2 plus 2 equals 5, then the whole thing is true. Right? Very nice. Now, yeah. I'm going to skip it. There are a couple of oh yeah, very nice. There's a very nice example. I'm not going to do it on. So check the proposition A 2 3. Let me check the number on the book, and I think it was the following one. Yes, and A 2 4. Check those two, and also the next one, 2.5, when you have the time, because I don't want to spend a lot of time on this, and you can do it on your own. What I want to say now is the following. We have been seeing with these implications that our hypothesis, if you assume that the hypothesis is true, then you have the right box, A and B. Okay. Now, it is very important to understand that this is not the same as B, then A. These are two different things. For instance, if x equals 2, then x squared equals 4. This is true. This implication is true. because true implies true. But if x squared equals 4, then x equals 2 is false, because true does not imply something which is false, because it could also be -2. So these two statements, this statement and this statement, are called converses. Okay. So yeah, let me see. Yeah. So this is, of course, connected to the if and only if statement. For instance, you can say, wait a moment. You can say that x equals 2 if and only if 2x equals 4. Because if x equals 2, then 2x equals 4. While if 2x equals 4, then x equals 2, right? So you can go in this direction, you can go in that direction. So this statement here is true only and only if this statement here is true. Okay. And if one is false, then the other must be false. You can say that this statement and that statement are equally true instead of A if and only if B. And there's also the possibility of working with the following, saying if the statement A, is false, then this statement B is false. This is sometimes called the inverse of if A is true, then B is true. Anyway, and this is very useful because it helps you to to work with when you want to prove a theorem. Sometimes you can use the technique of proof by contradiction, or in Latin reductio ad absurdum, which is, okay, if I am departing from something which I know that is true, then what I derive must be true. So it is what we have been using. Okay, let's move on a little bit. Yes, do you have any questions? Because I think this is by now everything that I wanted to tell you about logic, and we will go back to set theory. So this is by now the end of logic, and you can stop recording, I guess.